Hello everyone, thanks for watching this video. Today I am going to give a brief introduction about my work. The title is Discrete Cosine Transform Network for Guided Depth Map Super Resolution. As we all know, depth map and depth prediction are very useful for autonomous driving and robotics. Unfortunately, due to the technical limitations and the diversity of imaging environments, depth images often have the disadvantages of low resolution and noisy. However, in the same scene, with the acquisition of depth images, high-resolution and clear RGB images are relatively easy to obtain. In this task, the goal is to use high-resolution RGB images to provide extra information on edges and object contours, so that low-resolution depth maps can be upsampled to HR1s. Different from natural image super-resolution, depth image super-resolution needs to infer textureless and piecewise regions with sharp depth discontinuities. So the challenges of this task is that RGB texture overtransferred, which including the edge mismatch or overtransferred between the RGB depth image, the natural priors is difficult to learn effectively, along with the typical shortcomings of deep learning to explain the internal working mechanism. In response to the above-mentioned challenges, we propose Discrete Cosine Transform Network. We can call it DCT-Net. Our DCT-Net consists of 4 components, namely Semicoupled Feature Extraction Module, Guided Edge Spatial Attention Module, Discrete Cosine Transform Module, Depth Reconstruction Module. The ELA depth map and the HR-RGB image are paired into the encoder, and pass through these modules, and the final predicted HR depth map is reconstructed by the decoder. Then we give the detailed illustration of DCT-Net. We denote R and L for the RGB and ELA depth. H is HR depth we wish to obtain. It can be obtained by minimizing the following optimization function. The data fidelity item makes H and L close. L of R is the Laplacian filter imposed on R. W of R can be regarded as a given threshold function to select the edges useful for SR. We consider this equation as a discretization of 2D Poisson equation, and the solution can be figured out by utilizing the DCT operation. However, the tradition optimization method has 3 shortcomings. First, although H can be solved by optimization, it requires additional edge perceptual methods to determine W. Second, the lambda is manually given, which lacks flexibility. Third, the optimization of a single channel in the image domain is not enough to model the cross-modal internal feature correlation. So we will propose an advanced DCT-Net to integrate the DCT operation into CNN architecture to alleviate the above problems. First, we claim that RGB and depth maps have redundant information, example, shape and edges, and complementary information, example RGB texture details and depth image discontinuities, so we use p-semicoupled residual blocks that can extract shared private features from the source images effectively. Different from tradition residual blocks, convolution kernel here is semicoupled, which means that parameters in shared kernels are shared and those in private kernels are do not shared. Then, the RGB feature is employed by the JSON module to highlight the edge information useful for SR task. The attention module we employed is RFANet in CVPR 2020, which claims to make full use of the residual features. Subsequently, multi-channel RGB depth features and the edge attention weights are input into the DCT module, which implement DCT algorithm in each channel of feature to substitute learning the map between LR to HR feature in other methods. So in DCT module, we'll accomplish the SR task channel by channel without the learning-based CNN. Finally, the HR features are input into the depth reconstruction module to predict the HR depth map from its feature map via a simple CNN network. Quantitative comparison shows the excellent performance of DCT-Net under multiple datasets and different downsampling scales and can surpass SOTA methods in these 4 metrics. Error maps show that our depth SR results have lower prediction errors than other methods. Then we exhibit the highlighting edge weights output by the attention module. Obviously, after the attention module, the edge contour of the object is effectively highlighted and the texture information inside the object is eliminated, which can alleviate the issue for texture overtransferred. Our tuning parameter becomes a sequence of learnable parameters instead of manually given ones, and the flexibility of our model is further improved. It shows our model is more suitable for the characteristics of different data domains.